Amidst the boundless panorama of the cosmos, we teeter on the cusp of groundbreaking revelations that promise to revolutionize our perception of the universe. The arrival of the James Webb Space Telescope expands the reach of our celestial exploration, probing deeper into the mysteries of space and time than ever thought possible. Embarking on this uncharted voyage through Jost's discerning eye, we're offered an intimate look at the enigmatic early universe, thereby defying conventional astronomical paradigms. As we venture into this enlightening domain, the mosaic of our understanding unfurls, unveiling intricate designs and concealed complexities. Join us as we dig deep into how James Webb just detected massive structures that shouldn't exist. Can you imagine peering into a time machine revealing stories from eons ago? Well, the James Webb Space Telescope has done just that. Its first deep-field image, composed of a mosaic of 690 individual frames, portrays a patch of sky in the vicinity of the Big Dipper's handle, approximately 8 times larger than its predecessor. It's like holding a massive interstellar jigsaw puzzle where each piece is an individual galaxy from the early universe. These images present an intricate ballet of galaxies, some of which existed merely hundreds of millions of years after the Big Bang. Their faint glows, a silent testament to their distance and age, were unveiled by the unparalleled infrared sensitivity of Jost's near-infrared camera. This marked a monumental leap in cosmic exploration, providing an unprecedented look back into the universe's nascent epochs. Up to now, perhaps the greatest revelation in the past 100 years of studying the universe is that our home changes and evolves with time. And not just in minor, insignificant ways like stars moving about, gas clouds compressing, and massive stars dying in cataclysmic explosions. No. Our entire cosmos has changed its fundamental character more than once in the distant past, completely altering its internal state at a global, that is, universal, scale. Take, for instance, the fact that at one time in the foggy, ill-remembered past, there were no stars. We know this simple fact because of the existence of the cosmic microwave background, a bath of weak but persistent radiation that soaks the entire universe. If you encounter a random photon, a bit of light, there's a good chance it's from the cosmic microwave background. That light takes up more than 99.99% of all the radiation in the universe. It's a leftover relic from when the universe was just 270,000 years old and transitioned from a hot, roiling plasma into a neutral soup with no positive or negative charge. That transition released white-hot radiation that, over the course of 13.8 billion years, cooled and stretched down into the microwaves, giving us the background light that we can detect today. At the time of the release of the cosmic microwave background, the universe was about 1/1,000,000th its present volume and thousands of degrees hotter. It was also almost entirely uniform, with density differences no bigger than 1 part in 100,000. So, not exactly a state where stars could happily exist. In the millions of years following the release of the cosmic microwave background, affectionately known as recombination in astronomy circles, the universe was in an odd state. There was a persistent bath of white-hot radiation, but that radiation was quickly cooling as the universe continued its inexorable expansion. There was dark matter, of course, hanging out minding its own business. And there was the now neutral gas, almost entirely hydrogen and helium, finally released from its struggles with radiation and free to do as it pleased. And what it pleased to do was to hang out with as much of itself as possible. Thankfully, it didn't have to work very hard. In the exceedingly early universe, microscopic quantum fluctuations enlarged to become merely small differences in density. And why that happened is a story for another day. These tiny density differences didn't affect the greater cosmological expansion, but they did impact the lives of that neutral hydrogen. Any one patch that was slightly denser than average, even by a tiny, tiny bit, had a slightly stronger gravitational pull on its neighbors. That enhanced pull encouraged more gas to join the party, which amplified the gravitational tug, which encouraged even more neighbors, and so on. Like loud music at a house party acting as a siren song to encourage more revelers, over the course of millions of years, the rich gas got richer, and the poor gas got poorer. Through simple gravity, tiny density differences grew, building the first massive agglomerations of matter and emptying out their surroundings. Somewhere, someplace, some chunk of neutral hydrogen got lucky. Piling layers upon overwhelming layers on itself, the innermost core reached a critical temperature and density, forcing the atomic nuclei together in a complicated pattern, igniting a nuclear fusion and converting the raw material into helium. That ferocious process also released a little bit of energy, and in a flash the first star was born. For the first time since the first dozen minutes of the Big Bang, nuclear reactions took place in our universe. New sources of light dotting the cosmos flooded the once empty voids with radiation. These new sources of radiation recharged the neutral hydrogen that filled the universe during the so-called epoch of reionization. Through gravity, larger and more complex structures grew, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The astronomer Edwin Hubble figured out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Think of the universe as a loaf of raisin bread. It starts as a mixture of flour, water, yeast, and raisins. When you combine these ingredients, the yeast begins respiring and the loaf begins to rise. The raisins within it stand, inns for galaxies, stretch further apart from one another as the loaf expands. The Hubble telescope saw that the loaf is rising ever faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration appears to be driven by the repulsive energy of space itself, so-called dark energy, which is represented by the Greek letter L, pronounced lambda. Plug values for L, cold dark matter, and regular matter and radiation into the equations of Albert Einstein's general theory of relativity, and you get a model of how the universe evolves. This lambda cold dark matter. One way to test this picture is by looking at very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. However, as scientists used James Webb to delve into the first chapters of the universe, they found something that shouldn't exist. These unexpected discoveries then put scientific community in a dilemma, in that they will have to question the very fundamentals of what they know about cosmology. Specifically, almost immediately after the Webb Telescope fully switched on in July 2022, James Webb's unprecedented infrared sensitivity revealed the faint glows of galaxies, apparently from the far distant universe that had formed just hundreds of millions of years after the Big Bang. Astronomers had expected such landmark results to emerge more gradually. However, more than expected, there was an explosion of data. Those early results came about so quickly because researchers used a clever shortcut to estimate galactic distances. Astronomers usually pin down cosmic coordinates via precisely measuring redshift, a stretching of a galaxy's light toward the red end of the electromagnetic spectrum, as a result of the universe's expansion. But this requires the act of assembling and analyzing a galaxy's spectrum, a time-consuming and subtle process known as spectroscopy. The James Webb Space Telescope, fire hose of discovery, was instead powered by cruder, faster photometry-based techniques that essentially use obvious variations in galaxies' brightness to estimate their redshift. Thus, while the photometric results came thick and fast last summer, the spectroscopic results have only just begun trickling out. Already, though, with spectra-based distances in hand from only about a dozen candidates, researchers are finding that most measurements are matching the early photometric results. The latest, published in Nature Astronomy, confirm earlier distance estimates for 4 more galaxies identified by the JOST Advanced Deep Extragalactic Survey. According to Emma Curtis, Lake of the University of Hertfordshire in England, who led the spectroscopic results study. We've been waiting decades for this. To be able to do it within the first few months of this telescope was just incredible. Of the four, the most distant is one with the somewhat unwieldy name JADES, Gs, 0. It has a redshift value of 13.2, meaning we are seeing the galaxy as it appeared just 320 million years after the Big Bang. That high redshift makes JADES, Gs, 0, the most distant currently known in the universe. A record that the James Webb Space Telescope seems set to imminently break again, but one that highlights why astronomers are so thrilled. We now know for certain we are probing an era of the universe no human has ever laid eyes on before. It's astonishing, says Pieter van Dokkum of Yale University. This galaxy, he evocatively notes, is only slightly older from our perspective than the total time sharks have existed on Earth. Some 300 million years. In other words, you go from nothing to these fully formed galaxies in the blink of an eye. However, not all high redshift candidate galaxies have been so lucky, which highlights astronomers' early caution. In July, another survey called the Cosmic Evolution Early Release Science Survey, led by Finkelstein, spied a possible galaxy at a redshift of 16.4, just 240 million years after the Big Bang. Subsequent spectroscopy has shown that deduction was wrong, as revealed in late March in research led by Pablo Arrabal Haro, an astronomer at the National Science Foundation's NOR lab. The galaxy is actually a dusty imposter located at a redshift of 4.9, a still impressive but not at all record, breaking 1.2 billion years after the Big Bang. High levels of star formation are thought to have muddled early photometric analysis. As Colm Donnan of the University of Edinburgh in Scotland, a co-author on the work, explains, we can be easily fooled by contamination. A high redshift galaxy can be mimicked by a lower redshift galaxy with different features. The good news is that this particular galaxy appears to be a unique case, Donnan says. The same study was able to confirm that two other candidate galaxies did not have the same problem. One of these is Maisie's galaxy, which is seen at a redshift of 11.4, about 400 million years after the Big Bang. Now that such galaxies are being confirmed, their scientific implications can be more fully explored. These galaxies are small, many times tinier than the Milky Way, but some appear extremely bright and massive and have high star formation rates similar to that of our galaxy, which forms roughly one new star every year. While the galaxies don't yet pose problems for leading models of cosmology, they suggest galactic formation began earlier and proceeded faster than expected in the universe, which theorists had previously predicted began churning out galaxies at the ripe age of 1 billion years after the Big Bang. We're seeing a rise of massive galaxies faster than we thought previously, says Fabio Pacucci of the Harvard Smithsonian Center for Astrophysics. The ages of some of these early galaxies are estimated at just tens of millions of years. This could have implications for large structures of dark matter known as halos that sculpted early galaxies and for the nature of dark matter particles themselves. Like Sandra Tacella of the University of Cambridge says, one of the big open questions is, what is dark matter? The first generation of galaxies is a sensitive probe for different dark matter models. Some problematic, and potentially model-busting. Early universe candidate galaxies still remain. First among them may be a class of galaxies identified by Ivo Labbé of the Swinburne University of Technology in Australia and his colleagues. The team found galaxies with billions of solar masses, comparable in weight to the Milky Way, from just an estimated 750 million years after the Big Bang. These galaxies are 10 to 100 times bigger than galaxies previously seen in this era and are packed into structures 30 times smaller than the Milky Way. They're small, but they're massive, says Labbé, who says JOST is continuing to find similar galaxies essentially anywhere it looks deeply in the sky. For now, the galaxies have only been studied by photometry, with spectroscopic analysis planned for July. But the photometric success of other JOST results so far suggests Labbé and his colleagues' preliminary analysis is correct. as Michael Boylan, Colchin of the University of Texas at Austin, who was not involved in the JOST observations discussed in this article. The most extreme galaxies there still seem to pose a problem. Some of these systems would have to be forming stars 1,000 times as fast as the Milky Way. Question is that an impossibly high amount of star formation? The field continues to change rapidly as Webb is delivering more and more high redshift candidates. New evidence from the Webb Space Telescope continues to upend what scientists believed they knew about galaxies in the early universe. Our previous best views of the early universe, using tools such as the Hubble Space Telescope, didn't show clear disk-like structures in early galaxies. So astronomers thought maybe disk galaxies, similar to our own spiral Milky Way, were too fragile to exist during the universe's active early days. But the University of Manchester announced new research on September 22, 2023, suggesting that disk galaxies are 10 times more common in the universe's early years than once thought. Scientists already knew disk galaxies were common in the nearby universe, so the data showing a profusion of them in the early universe mean disk galaxies dominate the universe. Scientists from the University of Manchester and University of Victoria in Canada collaborated on this research. They published their peer-reviewed study in the Astrophysical Journal on September 22, 2023. The Milky Way galaxy is a barred spiral galaxy with an overall shape like a pancake. Astronomers already knew this type of disk galaxy was the most common in the nearby universe. And importantly, studies have shown that spiral or disk galaxies may be the most likely type of galaxy to host intelligent life. But astronomers didn't believe that this type of galaxy was common in the early universe. That conclusion was based on data from observatories such as Hubble. Therefore, they surmised that maybe the disk shape was too fragile to exist in a young universe where galaxies frequently interacted and merged. However, new data from Webb shows that disk galaxies were common even 10 billion plus years ago. Co-author Christopher Consolis of the University of Manchester said, "Using the Hubble Space Telescope, we thought that disk galaxies were almost non-existent until the universe was about 6 billion years old. These new Webb results push the time these Milky Way-like galaxies form to almost the beginning of the universe, and that is changing our complete understanding of how galaxy formation occurs. These results also suggest important questions about dark matter in the early universe, which we know very little about. Based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years. That's no small task, but it means there's much more exciting science to come. At that time, it could be said that all these discoveries, James Webb Space Telescope, bring us to crossroads of sorts. The lambda cold dark matter, the currently accepted cosmological model, is being put to the test. This model, while successful in explaining many cosmic phenomena, is coming under scrutiny due to the size and mass of the earliest galaxies, observed by James Webb Space Telescope. If you think about it, it's a bit like having an old map that's been accurate so far, but is now showing discrepancies. But that's not the end of the story. Artiega, a PhD student at the Cosmic Dawn Center, has thrown a fresh perspective into the mix. Instead of considering the entire galaxy as a single entity, she looked at galaxies on a pixel. By pixel basis, this approach resulted in infrared stellar masses up to 10 times larger than the standard approach. It's like zooming into a detailed painting to appreciate its intricacies. But let's take a step back. Studying distant galaxies isn't as simple as peering through a cosmic magnifying glass. Factors such as potential underestimation of observed epochs, overestimation of stellar masses, and even the chance discovery of the most massive galaxies at that time can skew our interpretation. Additionally, the difficulty in discerning individual stars in these distant galaxies adds another layer of complexity. Astronomers are continually searching for alternative signs and signals that could provide deeper insights into these enigmatic cosmic entities. For instance, the hunt for signs of stellar winds or supernovae is an ongoing process. The discovery of such signals could reveal the hidden engines that fueled the rapid growth of these early galaxies. On this thrilling journey of cosmic exploration, each new piece of data not only contributes to a more nuanced understanding of our universe, but also opens the door to more fascinating questions. As we peel back the layers of the cosmic onion with the juice, there are certain expectations and challenges that lie ahead on this astronomical expedition. Let's navigate through this new frontier together, understanding the collaborations that promise new discoveries and the emerging concerns about data accessibility. The beauty of our quest to understand the universe is that it's a shared journey. The exploration of the cosmos isn't confined to a single telescope or a single space agency. It's a collaborative endeavor, where various programs and instruments come together to provide a more comprehensive picture of the universe's grand tapestry. The Cosmos Webb Survey, for instance, is a highly anticipated initiative set to expand our understanding of high redshift galaxies. By working in tandem with James Webb Space Telescope, the survey will help identify more candidates for detailed study, ultimately unveiling an even more profound understanding of the early universe. Similarly, a promising collaboration lies on the horizon with NASA's Nancy Grace Roman Space Telescope. With its wider field of view, the Roman Space Telescope can help identify protocluster galaxy candidates. James Webb Space Telescope can then follow up with its high-resolution infrared tools, providing precise spectroscopic confirmation. These cooperative missions, where each instrument plays to its strengths, promise to deliver unprecedented insights into the origins and evolution of galaxies. While the James Webb Space Telescope has opened a treasure trove of information for astronomers, an emerging issue relates to data accessibility. The rapid availability of James Webb Space Telescope data has sparked some concerns within the scientific community. Some researchers feel frustrated, believing they've been scooped by others who have quicker access to the telescope's observations. This issue underscores the need for a balance between swift data release, which benefits the entire scientific community, and protecting the interests of the teams who propose the observations. As the James Webb Space Telescope continues to peer deeper into the universe, finding a solution that promotes collaborative research while respecting individual efforts is an essential challenge to tackle. Navigating this path will be crucial in fostering a supportive environment where knowledge and discovery can flourish. Besides challenging the standard model of cosmology, James Webb takes a jab at the mystery of the universe's expansion rate. Images from the James Webb Space Telescope have confirmed that the universe appears to be expanding significantly faster than it should be. Researchers report in a study, accepted in the Astrophysical Journal. The observation is in conflict with an esteemed theory, the standard model of cosmology, that describes how the universe has evolved since the first moments after the Big Bang. The conflict comes down to calculations of the Hubble constant, a number that describes how fast everything in the universe is flying apart. One calculation, based on Planck's satellite observations of the oldest light in the universe in conjunction with the standard model of cosmology, suggests the Hubble constant is 67.4 kilometers per second per megaparsec. A megaparsec is about 3 million light-years. Hubble Space Telescope images of stars at various distances from us provide a fundamentally incompatible value, 73 kilometers per second per megaparsec. The discrepancy is known as the Hubble tension, and new JOST data hasn't done anything to ease it. The telescope took images of the same stars as the Hubble telescope and calculated a very similar Hubble constant. Although the Planck number disagrees from the Hubble telescope and James Webb Space Telescope number by less than 10%, the discrepancy in the measurements implies that there's something terribly wrong with our understanding of the universe. Unless an error turns up in one of the measurements, it will take strange new physics to explain the tension. Papers in the literature over the last 10 years have invoked anything from weird dark matter to weird dark energy to another exotic-y particle, to a magnetic field in the early universe to a new field. All kinds of things. To explain the Hubble tension, says cosmologist Adam Riess of Johns Hopkins University, some of these explanations look semi-successful. Some of them look like failures. Some of them would cause other problems, he says. Developing a theory that might resolve the tension is still very much in the skunkworks, or extremely speculative stage of trying to understand what tension could mean. With the Hubble Telescope and James Webb Space Telescope, astronomers calculate the Hubble constant by observing flashing stars known as Cepheid variables. The stars flare up periodically at rates that indicate how much light they're putting out. Comparing a star's brightness in telescope images with its expected brightness, based on the flare-up rates, gives a measure of the distance to the stars. Shifts in the color of the light coming from the stars reveal how fast they're moving. Combining distance and speed observations of Cepheid stars leads to a measure of the expansion of the universe. But Cepheid variable stars tend to sit deep inside galaxies, surrounded by crowds of other stars. That can make it difficult to get good measurements of the Cepheid speeds and locations. One simple resolution for the Hubble tension could have been that the Hubble telescope measurements were simply off. Enter James Webb Space Telescope, which can peer through the stellar crowds to clearly make out the color and brightness of Cepheid variables. The higher resolution JOST images provide data with dramatically lower uncertainties and reduced confusion with nearby stars than the Hubble telescope could manage. The result: the Hubble telescope measurements have been right all along, Rias and colleagues report in their new paper. This study alone isn't enough to convince astronomer Wendy Friedman of the University of Chicago. The two galaxies studied are comparatively close to us, on cosmic scales, with the farthest one about 75 million light-years away, she notes. The relative proximity makes it easier to pick out the Cepheids from the stellar crowds. Friedman suspects it will be harder to distinguish Cepheids from the crowds of surrounding stars in more distant galaxies, even with JOST. The problem is only going to be worse, Friedman says. Because the resolution, it gets worse as you go to a higher distance. For very distant galaxies, she suspects, stars could appear too close together to pick out the Cepheids from neighboring stars, even for James Webb Space Telescope. As a result, Friedman says that Rias's confirmation of the higher Hubble constant may crumble with analysis of more distant Cepheids. Hints that the measurements might hold up at larger distances arose in a Sept. 12 presentation at a conference in Baltimore dedicated to the first year of JOST science. Rias showed preliminary Cepheid data from 4 more galaxies. One of them is 140 million light-years away, among the most distant galaxies in the Hubble telescope Cepheid studies. James Webb Telescope data from those stars also line up with the Hubble telescope measurements. Although still awaiting peer review, the images strongly suggest that the JOST has indeed overcome the uncertainties that resulted when light from Cepheids got mixed up with light from nearby stars in the lower resolution Hubble telescope images. University of Cambridge astrophysicist George F. Stathiou, who was not involved in the study, is both convinced that Rias has gotten the measurements right and confounded by the implications. When they showed me all of that data, F. Stathiou says, my reaction was, well, I'm stumped. F. Stathiou is a member of the Planck Satellite Collaboration, which studied the oldest light in the universe, called the cosmic microwave background, and found the lower value for the expansion of the universe. The satellite's calculation is based on images of patterns in light from the early universe. Together with the standard model of cosmology, the images show that the universe is expanding with a Hubble constant that's lower than the JOST measurement by about 5.6 kilometers per second per megaparsecond. As it stands, there doesn't seem to be anything wrong with the Planck measurement of the Hubble constant or with the JOST observations. The tension between the measurements points a finger at the standard model of cosmology as the problem. But the standard model also appears to be unimpeachable. It's withstood numerous other challenges without breaking down. The model came about in part due to the discovery of the accelerating expansion of the universe, which earned Rias and others a Nobel Prize in physics. The revelation was a key piece in shaping the model to include dark matter, dark energy, and other factors, making it the simplest theory that can accurately describe the universe. Now, though, Rias's Cepheid-based studies of the Hubble constant show that there's still more to learn. This is a crack, or a surprise that doesn't fit, Rias says. It's left us more in a kind of confused or purgatory state. The implication, he says, is there's a problem with the standard model. You can revise it, but we don't know how to revise it, which direction or in what way. People shouldn't mistake the tension over the Hubble tension as despair. It's more of an opportunity to learn something about the universe with these telescopes, Rees says. One possibility is completely new physics. According to Friedman, if there's new physics, that'd be fun. We'd all like to see something new and interesting. Either way, I think it's going to be an exciting result. Either confirming the standard model or showing that there's something still in the model that's missing. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.